All right, here we go. These are the problems from worksheet 4.1b. All right, so here we go. We got a crate that's being pulled on a horizontal sidewalk. So this time I give you the weight. So here's the weight of the crate. That rhymes. We got 768 newtons. It's being pulled along a long horizontal sidewalk at a constant speed. Holy cats, that is super important because that tells us that the net force on this guy is 0. Alright, it's being pulled by a rope, so here we go, force of tension, right? Over here it tells us that the force is 243 newtons, and here it tells us that it is at an angle of 41 degrees above the horizontal. So we should probably figure out how much tension there is in the x direction and how much tension there is in the y direction. So we're just going to do some trig. So this guy is going to be 243 times the sine of 41 degrees. And this one's going to be 243 times the cosine of 41 degrees. So let's see what that gets. All right, so I filled in those values here. The y component ends up being 159.4 newtons, and the x component is 183.4 newtons. So let's go over here and add those to our drawing. So we're going to have a tension force in the x direction that is 183.4 newtons. And we're going to have a tension force in the y direction, which is 159.4 newtons. All right, let's see, we know it's going at a constant speed, and we certainly know it's not moving up or down at all. So we find our normal force. So what we need to do is we need to ensure that our normal force plus this vertical tension force cancel out our force of gravity, which I probably should have made negative. Sorry if that's bothering me. So we've got 768 down, but only 159 up, so let's figure out how much we're missing. So I'm just going to do 768 minus 159.4 to discover that this normal force is going to be 608.6 newtons. All right? And then finally, we know that it's moving at a constant speed. The fact that it's sliding tells us that it's kinetic friction. The fact that it's at a constant speed means the net force is 0. So this has got to be negative 183.4 newtons. So there's our drawing. And so, to find our coefficient of kinetic friction, we're just going to use the fact that we know this. Our force of kinetic friction is 183.4. That's got to equal our coefficient of friction times our normal force, which is 608.6 newtons. So divide, and then your coefficient turns out to be, hopefully, pretty close to 0.30. Smiley face. All right, there we go. So that's number 6. All right, number 7. So number 7 is basically just a vector addition problem. All right. So here's what we're going to do. We got these two kids that are trying to push a crate, and it says they want to push it in the direction marked X. So their goal is they want it to go this way. So here is what we know. We know that force 1 is 100 newtons at 60 degrees, looks like north of east, and that our F2 is 140 newtons at 30 degrees south of east. All right. So what we want to do is find the components of these things. All right. So what I'm going to do is we're going to make a little chart here, and for each of these forces, let's find our x and y components, just like we used to do when we were doing vectors a couple chapters ago. So let's see. All right. So to figure these out, let's see. The F1 ends up having an x component of 50 newtons, positive, and then a y component, which is really the one that I'm interested in, of 100 times the sine of 60. So it gives us 86.6 newtons. All right. Then, force 2, similarly, we're going to have an x component of 140 times the cosine of 30, which gives us 121.2. And more importantly, we have a y component of negative 70 newtons. All right. So then the question is, what does this kid need to do? So the force of the kid needs to be such that our y values add up to 0. Here's our net force. Now, the big thing to notice here is this, those are smiley faces, the x components don't really matter. I guess unless the kid had a very large negative x component, that would be problematic because that would be going the wrong way. But our goal is we want to find the smallest force the kid can exert. So if the kid exerts 0 force in the x direction, then we're good, because our net force then will be 171.2 newtons in the x direction. The real issue is that we need the y component to be 0. All right, and so in order for that to happen, you just got to figure out what do we need. Well, let's see. We got 86 positive and 70 negative. It looks like you need another 16.6 negative to make everything add up to 0. And there's your answer on that one. That's all you got to do. So really, to make this calculation, we don't even need all of this stuff. That was sort of extra business. All right? All right, let's see. What do we got next? Number 8. Roy is in trouble with the mob. Yikes! He's dragged, kicking and screaming by some thugs across the parking lot. He's got a mass of 76 kilograms. Alright, so here's Roy. Mass equals 76 kilograms. Alright, so we can go ahead and put in our force of gravity. It's going to be negative... somewhere I have an answer key here. Negative 744.8 newtons. And then, let's see what else do we know. We know that he's being pulled by his shoelaces. There's a little glitch here. It says, and they need a force of at least 345 newtons to get him moving. So here's the force of tension in his shoelaces, 345 newtons. We know that this is at an angle of, 40 degrees. So again, we're going to find the force of tension in the x direction, force of tension in the y direction. So just go through your trig. The x component ends up being about 264.3 newtons. And the force of tension in the y direction turns out to be about 221.8 newtons. Which means that we need a normal force of about 523 newtons. Alright? So, the next issue is this. That's the force needed to get him moving. So what that means is, what I know at this point, I'm going to erase this drawing here because it's not doing us any good. So I know that my maximum force of static friction is 264.3 newtons, right? In this scenario. And we know that our normal force is 523 newtons. So I think that if we divide, that'll give us our coefficient of static friction, right? And so that should hopefully give you pretty close to 0.5. Right, so there's your coefficient of kinetic friction for static friction. Oh, and I'm seeing now I wrote it wrong. It's 0.51. All right. So then in B, what happens? It says we're going to keep exerting this force. How far would the police have to drag Robert with a force of 340? Who is Robert? I don't know why Roy turned into Robert. This is Roy. And I think your form that you might have may say 350. I changed it to 345 here. The calculations for 350 are basically the same. Your numbers will be a scotch different. So just know that if it says 350 and you want to do the calculations with that number, then you're going to have to recalculate these two guys, right? Okay, but I'm not going to do that. So what we need to do is find our force of kinetic friction. So that's going to be our coefficient of kinetic friction times our normal force. So the coefficient is 0.4. Our normal force is 523. So our kinetic friction turns out to be 209.2 newtons. So we can put that over here in our drawing. And so now you can find your net force. It's simply going to be, 264.3 minus 209.2, because the only forces that don't cancel are the x component from the tension and the friction. So if you do that, you end up getting, what are we going to get? 55.1 maybe? Something like that. And then you can find your acceleration just by doing net force over mass. But that isn't what we're trying to do. Alright, so I actually need to get a calculator here and do this. So let's see. 264.3 minus 209.2 does in fact give us 55.1. I'm going to divide that by the mass to get the acceleration. So you get an acceleration of 0.725 meters per second squared. And then what are we trying to do? We're trying to figure out how far they have to drag him across the ground. So I'm going to use this guy. 2a delta x vf squared minus vi squared. So 2 times 0.725 times delta x equals our vf. The goal is to make our vf 10, and then our vi was 0. Solve this guy. We get 100 divided by like 1.45 or something like that. And hopefully that gives you 69 newtons. Let's see what we get. 100 divided by 2 divided by 0.725. Yep, 69 meters. Alright, there you go. That is number 8. Now, obviously, I'm going through these pretty quickly. If you need further assistance, you guys know I'm always around before and after school. Alright. So here we go. This guy, we got an 800 Newton crate. So again, I give you the weight of the crate. So force of gravity, 800 newtons, negative if you prefer. The arrow shows the same thing, which is why I'm not super religious about putting in those negative signs there. Alright, so he's going to be pulled by a force F at an angle of 30 degrees. So there's going to be an x component and a y component to that. Calculate those pretty easily. So in part A, this force is 450. So your, oh my gosh. Oh yeah, I'm good. So let's see, the x component turns out to be, it looks like this says 389 newtons. And then the y component ends up being, oh, this is terrible. I'm sorry. My drawing is upside down. He's being pushed, right? So the force is going to go this way. So my force is, what did I just say, 450 newtons. There's going to be an x component, which if you figure it out does turn out to be 389 newtons. There's going to be a y component, which is negative 225 newtons. This angle in here is still 30 degrees. So we've got our drawing over here. Force in the y component is negative 225. That means that there's got to be a normal force of 1,025 newtons. And we've got a force in the x direction of 389 newtons. So what we need to do is see if this is all enough to get the crate moving. So our force in static friction max is going to be the coefficient of static friction times the normal force. So our coefficient is 0.35. Our normal force is 1,025. Multiply this out and you get a number that I apparently don't have written down. So we get 0.35 times 1,025. So you get about 359 newtons. So it looks like 389 is bigger than our maximum friction. So now we got to go to kinetic friction. So that's going to be 0.25 times 1,025, which turns out to be 250, 1025. gives you about 256 newtons. So now I can go ahead and put that in over here. And so from here, we got to find, let's see, acceleration is net force over mass. So my net force is just going to be 389 minus 256, which is going to be 133 newtons, divided by our mass. Oh, we got to find the mass. Well, let's see. We know that our weight is 800 newtons, so the mass is just going to be 800 divided by 9.8, right? So that gives you about 81.6 kilograms. So divide that out, and it gives you about 1.6 meters a second squared. All right. So that is the deal with A. Now B is very similar. All right. So I'm going to cheat here because I can. Oops. All right. So I know all of that stuff still, but here's what's different, is that this force now is only 400 newtons, so that's going to change these guys. All right? So everything is kind of the same, except this force that's being applied is only 400 newtons. So what happens is, when you find your x component, you get 346 newtons. When you find your y component, you get negative 200. Which means that your normal force is exactly 1,000 newtons. So now when you find your force of friction static max, you're going to get your coefficient times your new normal force, and it gives you 350 newtons. And look over here, we only got 346 newtons trying to get this thing moving. So friction is like 346 newtons. What do you got? So friction comes over here and just exerts 346 newtons, which is exactly enough force make the acceleration and the net force both 0. All right. Okay. Finally, number 10. I'm not going to do number 11, by the way. I probably should have said that at the beginning of all this. So number 11 is more called than anything you'd see on a test. Okay, so here we go. In this one, we've got a 12 kilogram box being pushed. Alright, so what do we got? 12 kilogram box. Mass equals 12 kilograms. So right away I'm going to find my force of gravity. It turns out to be negative 117.6 newtons. It's being pushed from rest across a flat table by a horizontal force. I suppose that it's Roy, probably, 49 newtons, which causes the box to accelerate at 2.1 meters a second squared. Coefficient of static friction is 0.30. A says to make a free body diagram and find the coefficient of kinetic friction. So notice, too, I sort of glossed over this. This force was horizontal, so I don't even need to worry about angles here. So that means that this normal force is just going to be 117.6 newtons. Since I know my acceleration, I can find my net force. Oops. So we get a net force of 25.2 newtons. And so then the question is, what is the force of kinetic friction have to be? So what number plus 49 equals 25.2? So to figure that out, using a little bit of algebra, negative 23.8 newtons. And so now I can find my coefficient of kinetic friction, right? The coefficient of kinetic friction is the force of kinetic friction over the normal force. So I'm just going to divide 23.8 divided by 117.6, and it gives you really close to 0.20. So that's part A. Now, B says suppose the force was, B says suppose the force was exerted at 30 degrees above the horizontal, and C, you're exerting it at 30 degrees below the horizontal. This is actually pretty similar to other ones that I've done here in the video. The big thing to notice is that when you do the math, you exert your force this way, below the horizontal, you've got a y component that makes your normal force bigger, right? Because the normal force needs to compensate for gravity and that y component, all right? So that's why in C it doesn't move. There's so much, this bigger normal force makes your static force of static friction bigger, and it doesn't move, all right? I'm sorry, I am out of time. I need to get going here. But I'm happy to do these in class if you want. All right. Have a good one.